In this video, I am going to solve these four problems taken from the chapter 8, Potential Energy and Conservation of Energy, from the book Principles of Physics, 10th edition. First question. You drop a 2 kilogram book to a friend who stands on the ground at a distance d which is equal to 10 meters below. So you have to see this figure. Here two persons are here. One is exactly standing on the ground and another one is on the balcony. Clear? And here this person is going to drop the book, and the mass of the book is mentioned as 2 kilogram, and the distance from this book to the ground is mentioned as d, which is exactly 10 meter. Clear? Your friend outstretched hand at a distance d which is equal to 1.5 meter above the ground. So now in the second line they mention the information about this person, and he is exactly outstretched his hand, and from the hand to the ground the distance is mentioned as 1.5 meter. Clear? First question. How much work? Which work? The work done by the gravity. So how much work does the gravitational force do on the book as it drops to her hand? So if she is going to drop the book and she is going to catch that book, am I right? So when she is going to drop the book, what should be the gravitation force act on the book? Clear? And we already studied this information in the theory. We studied the rule, work done by the gravity which is equal to mg d cosine of theta. Clear? So this rule we studied. Am I right? So before that we have to write what is given in the question. They give the information about the mass of the book. The mass of the book is exactly 2 kilogram, and the distance from the person, that means who is exactly in the balcony, and from that distance to the ground they mention caps d, which is exactly 10 meter, and then the one who is exactly standing on the ground and she is exactly outstretched her hand, from her hand to the ground they mention as small d, which is exactly 1.5 meter. Clear? So now what you are going to find, we are going to find what should be the gravitation force do on the book. And we already studied this rule mgd cosine theta. So from this book, when you just drop, what will happen? This book is going to be in the direction of the gravity. Am I right? So that means in this chapter we studied only two rules. If any object is in the rising, in the upward direction, the theta is exactly 180 degree, and when the direction of the object is down towards the earth, which is exactly 0 degree. So now this question we are going to find the gravitation for the work done by the gravity. So from when she is going to drop the book, it is exactly towards the ground. That means it is exactly towards the direction of the gravity. So we have to consider for this question the theta, which is exactly 0 degree. Clear? And the most important thing, we have to identify the distance from this point to this person hand. Am I right? So that means we can easily find the distance. What's the distance? So exactly I'm going to write h. So here h is exactly caps d minus small d, which is exactly equal to 10 minus 1.5, which is 8.5 meter. Clear? So better I can modify this equation. So work done by the gravity, which is equal to mg h cosine theta. Clear? Now I'm going to substitute the value. The mass of the book is 2 kilogram, and the acceleration due to gravity value is 9.8. And from this point, which point? The one who is exactly on the balcony, am I right? So from this point to the person is outstretched her hand. So this distance is exactly h, am I right? So from this point to the hand, exactly h. So 9.8 multiplied by the h value is 8.5 multiplied by cosine of 0. Cosine of 0 is exactly 1. So we have to multiply these. 2 multiplied by 9.8 multiplied by 8.5 gives the value of 166.6, 166.6, and the unit of the work is exactly joule. So this is the answer for the first question. What is this question? What is the work done by the gravitational force on the book? Clear? Actually, this question has many subdivisions. So now we are going to answer one by one. And in the second part of the question, what is the change in potential energy in the gravitational potential? Actually, here delta U is nothing but the change in gravitational potential energy of the book Earth system during the drop. So that means we are going to calculate what should be the change in potential energy. As we already, I am going to write again. So this caps D is exactly 10 meter and this small d is exactly 1.5 meter. I'm right. And the distance from this point to this person hand is exactly 8.5. Clear? So now this height is exactly, the value is 8.5. So now if you want to find the change in potential energy, the change in potential, which is exactly equal to potential energy final minus potential energy initial, and we already know the potential energy formula is mgh, right? So now I'm going to apply this rule. So which one is the initial value? The initial value is this word, am I right? So this one is the initial point and this one is the final point. Clear? So I have to write mgh final minus mgh initial. Clear? So what is the height? The mass 2 multiplied by 9.8 multiplied by the height final. The height final is exactly 1.5. Am I right? From the ground to this person's hand is exactly 1.5. So 1.5 minus 2 multiplied by 9.8 multiplied by what is our initial height from the ground. Am I right? So from the ground to the initial point is exactly 10. So now I have to calculate one by one. First I am going to calculate the final potential energy. 2 multiplied by 9.8 multiplied by 1.5, which gives the value of 29.4 minus 2 multiplied by 9.8 multiplied by 10 gives the value of 196. So I have to subtract minus 29.4 is exactly again 166.6 joules, but the sign is minus. Clear? So in theory, what we studied in the theory, work done which is exactly equal to the work done which is exactly equal to the negative of change in potential energy. Am I right? So it's proved here, because the work done by the gravity, we got the positive value of 166.6 joules, but when we find the value of the change in potential energy, we got the negative value. That means the rule exactly works. Clear? Okay, now we have to answer the third question. So what is given in the third question? So read it carefully. If the gravitational potential energy of the system is taken to be zero at the ground level, so in the ground level, we are going to consider our potential energy is the ground level, the potential energy we are going to consider as zero, the ground level. Okay, what is the potential energy when the book is released? So that means this is our initial point, this is our final point, right? So they ask, when the book is released with respect to the ground, and in the ground you have to consider the potential energy in the ground level is exactly 0 joules, and you have to find what should be the potential energy when the book is released. Which position is the release point? The initial position. Am I right? So from here, from this point, the book is going to release. Am I right? So I have to write the rule. The potential energy for the initial, that means the book is released. So potential energy, but I can write UI, that means bracket, I can write in UI, the book is released, clear, which is equal to mghi. I'm going to write. So which one is I think better we can just write it's instead of writing hi, because we are going to consider the ground level. So this is not hi, so this is caps D, right? Because we are going to consider from the ground level. So from the ground level to the book point, the person is who going to hold the book is exactly D, capital D, am I right? Which is exactly 10 meters. So I have to consider this value. So I'm going to substitute the value for this mass of the book, 2 multiplied by 9.8 multiplied by the D value is exactly 10. So if I multiply 2 multiplied by 9.8 multiplied by 10, so I got the value as 196 joules. Clear? Okay. Fourth part. If the gravitational potential energy of the system is taken to be 0 in the ground level, so that means the ground level again the potential energy is 0. What is the potential energy when it reaches her hand? That means when after she dropped the book, this book is exactly reach the person who is exactly standing on the ground. So once the book reached her hand, okay, what should be the potential energy? That means this distance is exactly small d. Am I right? Clear? So I have to write potential energy final. Which is the final? The book reached her hand. Clear? So the formula for the potential energy is again mg. I have to write small d. Clear? Because the book is exactly, we are going to calculate the potential energy from the ground level. So the ground level to her hand is exactly small d. So 2 multiplied by 9.8 multiplied by 1.5. So 2 multiplied by 9.8 multiplied by 1.5. I got the answer as 29.4 joule. Clear? So this is the answer for the fourth part. So now we have to answer the fifth question. In this question, we are going to take the potential level in the ground level is exactly 100 joule. Again, you are going to calculate what should be the work done by the gravity. Clear? Work done by the gravity never change because we already found the answer here. Am I right? We already found the work done by the gravity here. Because even if you consider potential energy the ground level is 200 or 300, that doesn't matter because we already found the value for the gravitational potential energy with respect to the book and the earth system exactly. We got the answer as 166, right? So that means, so whether the potential energy the ground level change or not, that is not a matter. So whatever it may be, the gravitational, the work done by the gravitational with respect to the ground level is exactly 167, 166.6 we got. So again, you will get the same answer. Clear? So which is nothing but what we got, mg, this is h, am I right? H cosine of theta. So here h is nothing but caps d minus small d. Clear? So that means the caps d is 10 and small d is exactly 1.5. So you'll get 8.5 meter here. So when, and the theta here again it is coming towards the gravity, towards the ground, am I right? So theta is 0. So when you substitute the value here, again you will get 166.6 joule. Clear? Okay. Okay. Again we are going to consider the potential energy in the ground level is 100 joule. Again you have to find what is the change in potential energy. What is the change in potential? This is our initial point, this is our final point. Initial point from here to the ground and the final point from the ground to this person hand level. Am I right? That means d minus small d. So the change in potential energy, which is equal to mg caps d minus small d, and again you will get the same answer, negative value. Am I right? So sorry, small d minus caps d, because the position, initial position, final position minus initial position. So that means small d minus caps d. So mass of the book is 2 and the g value is 9.8 multiplied by, and the initial position is, sorry, final minus initial. Am I right? So the final position is exactly d. What's the rule? mg final yf minus mg y initial. Here y is nothing but, so this distance I mentioned. Clear? So that means the final position distance is small d and the initial position height is exactly caps d. So when you substitute the value, the small d value is 1.5 minus 10. Again you will get the negative value, because we studied the work which is equal to a negative of potential change in potential energy. So you will get minus 166.6 joule. Clear? Okay. In this question, we are going to take again the ground level potential energy is 100 joules, but you have to read the question very carefully. In this question, we are going to find what should be the value of the potential energy. Whenever you are going to calculate the value of the potential energy, by the time you have to add this value. Clear? So that means in the release point, what is the release point? This is the release point. Am I right? So this is the release point. This is the reached point. So this is released point. This is this value. This place is a reached point. So in the release point, we are going to find what should be the potential energy. So in the release point, which is nothing but potential energy initial point, which is equal to mg, this distance. Am I right? Clear? D plus the potential energy, because I want to I have to show the potential energy as u naught here. So multiplies u naught, because when the book, we are going to consider the release point, so that means we have to add this potential energy also. So what should be the value? 2 multiplied by 9.8 multiplied by the initial values d 10 plus the ground level potential energy is 100 joules. So when you calculate this one, 2 multiplied by 9.8 multiplied by 10, we got the value as 196. So only this part is exactly 196 plus 100. So the total potential energy from the release point to the ground level, because the question they clearly mentioned in the ground level the potential energy is 100. So whenever you are going to find the potential energy only, then only you have to add this. Clear? That means 296 joules. And in the last question, again, we are going to find what is the potential energy in the reached. That means when the book is reached to her hand. So potential energy final, which is equal to mg small d plus potential energy in the ground level. Clear? So that means 2 multiplied by 9.8 multiplied by the small d is 1.5 plus 100. So I have to multiply this part and then I have to add with 100. So 2 multiplied by 9.8 multiplied by 1.5. So I got the value as 29.4 plus 100, which is in the ground level. So the total answer, the total potential energy in the reached point, which is exactly equal to 100 plus 29.4 is 129.4 joules. Clear? So this is the answer for the First question. So in the first questions, we have the subdivisions from A to H. Clear? So the most important thing, if you want to answer these questions, because this question has many subdivisions, first of all, please identify the values from the figure. When you see the figure, then only you'll get the clear idea. So the most important thing, if you have any potential energy at the ground level, you have to add this potential energy only when you are going to find the potential energy only. Clear? So that means in this question we are going to find the potential energy for the initial condition. In this question we are going to find the potential energy for the final condition. But when you go for finding the potential energy for the change in potential energy, by that you should not consider that. Clear? Understand? Okay. Second question. A 1.5 kilogram snowball is fired from a cliff 11.5 meter high. So you are firing the snowball and the mass of the snowball is mentioned as 1.5 kilogram. Clear? And we are just firing to a height of 11.5 meters. So here the height is 11.5 meter high. The snowball initial velocity is 16 meter per second. So what is the initial velocity of the snowball? It's a 16 meter per second, and you are just directed with an angle of 41 degree above the horizontal. By using this, what we are going to find? We are going to find how much work is done on the snowball by the gravitational force during its flight to a flat ground below the cliff. So below the cliff, you have a ground. Am I right? So you are going to find what should be the work done. And we know the formula. When you fire, what will happen? It will go to the maximum height and it will be coming towards the ground. Am I right? So we know the W, the work done by the gravity, which is exactly equal to mgy cosine theta. And here the theta, don't get confused about this theta and this theta, both are different. Clear? Actually this is the shooting angle, because you are firing the snowball with respect to some angle, so don't get confused. Here better I can use phi here. Okay, so better instead of this theta, better I can use the angle phi. So what is the angle here? The angle is exactly, once it reaches the maximum height, it will coming towards the ground. So that means the total angle is exactly 0 degree, right? So the angle phi is exactly 0 degree. So now I'm going to substitute the value. The mass of the snowball is 1.5 kilogram multiplied by 9.8 multiplied by the height. How much height maximum it gone? 11.5, and cosine phi angle is 0. So cosine of 0 is exactly 1. So now I'm going to multiply all these, and once you multiply, you will get the answer for the work done by the gravity on the snowball. Clear? So 1.5 multiplied by 9.8 multiplied by 11.5, I got the answer as 169.05. 169.05, and the unit is joules. Clear? So this is the answer for the first question. And this question has a second subdivision also. And in the second part, what should be the change in gravitational delta U for the snowball earth system during the flight? And in the theory, we studied the rule work done which is equal to, that means the work done by the gravity which is equal to the negative of change in potential energy, right? So now we are going to find what is the change in potential energy, but in the first part we already identified what is the work done by the gravity. Clear? So that means the rule work done by the gravity which is equal to the negative of change in potential energy. Therefore the change in potential energy which is equal to the negative of work done by the gravity. So I can take the answer from the first part. So what is the answer in the first part? We found the answer for the work done by the gravity is exactly 169.05 joules. 169.05 joules. So therefore the delta U, which is equal to minus of 169.05 joules. Clear? This is the answer for the second part. Now we have to answer the third part. If the gravitational potential energy is taken to be zero at the height of the cliff, so here the ground and here you have the cliff, that means it's like a small cliff, and from this you are just firing the ball. So let's we take the fire from the ball height, it reached the maximum height, and what should be the distance from the ground to this is exactly 11.5 meter. So what is this is our initial point, am I right? So in the initial point they said you have the initial potential energy is zero. Clear? So now we have to find what is the value when the snowball reaches the ground. So that means we are going to find what should be the final value. Clear? So that means the change in potential energy, which is equal to the final potential energy minus initial potential energy. The initial potential energy we just going to take as zero. So therefore, my final potential energy, I have to use this value. So the value is exactly, so delta U, which is equal to UF. Therefore, my UF, that means the final potential energy, which is having the same value of change in potential energy. Am I right? So in the first part, we already, that means in the second part of the question, we already found the value of the change in potential energy. So what is the answer here? The answer for the final potential energy, when the snowball reached the ground, it has the potential energy value of, what's the value? I'm going to take the data from the second part. So in the second part, we got the answer as, what's the answer? Minus 169.05. Clear? So that means the answer for the third part is exactly minus 169.05 joules. Clear? Third question. A 5-gram marble is fired vertically upward using a spring gun. So you have a spring gun and you are just pressing the spring and you are just putting the 5 grams of marble inside and you are shooting the marble exactly vertically upward direction. And the spring must be compressed 8 centimeter. And when you compress, that means the x value, that means how much you are compressing the spring, how much you are pushing the spring in the inward direction. So that means how much level you are compressing the spring, up to 8 centimeter level you are just compressing the spring. And by that, when you shoot, how much height the marble ball is gone, it is going to a height of 20 meters. That means the total height reached by the marble is exactly 20 meter. Clear? And what is the mass of the marble? The mass of the marble is 5 gram. So I have to convert these in terms of kilogram. First question, we are going to find what is the change in gravitational potential energy of the marble earth system during this 20-meter ascent. So we are going to find the change in potential, the gravitational potential energy. And better I am going to write, so this is our earth and you are just shooting the marble goes to this height, and the initial, it's reached the height from this point to this point. The total height is mentioned at 20 meter. Clear? So we are going to find what should be the change in potential. So final minus initial. So final here is nothing but, because you are shooting from the ground level. So this is your initial point. This is your final point. So this is the final. This is the initial point, because you are shooting the marble from the ground level. Am I right? So we are reaching the height of 20 meters. So we know the rule, change in potential, which is equal to mg height final minus height initial. Am I right? So height initial is 0, height final is 20 meters. So if you substitute the value, the mass of the marble is 5 multiplied by 10 to the power of minus 3 multiplied by 9.8 multiplied by 20 minus 0. So we got the answer. So I have to calculate, multiply 5 multiplied by 10 to the power of minus 3 multiplied by 9.8 multiplied by 20. I got the answer as 0.98. So what's the answer? 0.98 joules. So this is the answer for change in gravitational potential energy. Clear? Second part. What is given in the second part of the question? What is the change in elastic potential energy of the spring during its launch of the marble. So that means here we have to use the conservation of the mechanical energy. Am I right? So what we studied in the theory? Change in gravitational potential energy plus change in elastic potential energy, which is equal to 0, right? So that means we are going to find the value of this change in elastic potential energy. Therefore, the change in elastic potential energy, which is equal to negative of change in gravitational potential energy, right? So we in the first part we already found the answer for the change in gravitational potential energy. So I can use this answer here. So therefore, the change in elastic potential energy, which is equal to negative value of 0.98 joules. So this is the answer for the second part. Clear? The third part. What we are going to find in the third part? What is the spring constant of the spring? So because you are using the spring gun, am I right? So you are compressing the spring to 8 centimeters. So how much level you are compressing the spring? 8 centimeters. So if you convert that in terms of meter, 8 multiplied by 10 power minus 2 meter. So now we are going to identify what should be the value of the spring constant K. Clear? So for that, I'm going to use the formula for the elastic potential energy, right? So the elastic potential energy, which is equal to the elastic potential energy or spring potential energy, which is equal to half k x square. So this is the rule, am I right? So now we are going to find what should be the value of the k. So you have to rearrange this equation in terms of spring constant. Therefore, k, which is equal to 2 multiplied by the elastic potential energy over x square. Clear? So now I'm going to substitute the value, because when you are compressing the spring, by the time the potential energy is taken to 0, when it goes to the maximum height, so you have the final elastic potential energy, right? So therefore 2 multiplied by the potential energy we have to take as 0.98 divided by 8. The compression of the spring is 8 centimeter, so 8 multiplied by 10 power minus 2. So if you multiply and divide, you'll get the value of the spring constant. So 2 multiplied by 0.98 divided by 8 multiplied by 10 power minus 2 square, right? The whole square. So the answer I got is 306.25. And what's the unit for the spring constant? Newton per meter. So this is the answer. Clear? This is the answer for the third part. Okay, now we have to move to the fourth question. A 4 kilogram bundle starts up 30-degree incline with 150 joules of kinetic energy. That means you have a bundle and which is moving from bottom to top. So they mention starts up. That means upward side in the incline, the bundle is moving. Am I right? So better I can draw the diagram. So I have to draw the diagram. So it's the ground level and this is the incline, which is projected to an angle of 30-degree, right? And then here you have the bundle. Here you have the bundle. So what is the mass of the bundle? The mass of the bundle is given 4 kilogram. So this is the mass of the bundle, which is 4 kilogram, and it is moving in the upward direction. So starts up, clear, with the initial kinetic energy. What is the initial kinetic energy? The kinetic energy initial is given as 150 joules. How far will it slide up the incline? So how much distance this block will be moving? So that means when the block is moving upward direction, let's we take the block reach this point. Okay, let's we take the block reach this point. And when the block reach the maximum point, that means this is the final position. Am I right? So what is the kinetic energy final in this point? the kinetic energy final in this point, because the speed will be stopped, so your kinetic energy will be, the kinetic energy, the final state is 0, right? Now I have to draw the free body diagram, so better I can use the color pen, so by that you will get a clear idea. So I have to draw the free body diagram. Why I have to draw the free body diagram? Because you are going to find something, because the coefficient of kinetic friction is given. So first of all, we have to identify what is our free body diagram. So this is your normal force, right? And this is the force due to gravity, which is mg, and this is the x component of the gravity, which is mg cosine theta, and this one is the mg sine theta, and here you have friction force, kinetic friction. Clear? So this is our free body diagram. So now we have to answer one by one. So what they ask, if the kinetic friction coefficient of the bundle between the bundle and the incline is 0.6, that means they give the value of the kinetic coefficient. That means kinetic friction coefficient of kinetic friction, mu k, because it's a unitless, am I right? So the mu k value is given for the bundle and the incline, which is exactly 0.36. We have to find how far will it slide. So that means from this initial position to the final position, how far this block will move. That means we have to find the distance. Clear? From this point to this point. Actually, this is d. Okay, so better I can write one more time. So this is this distance we have to identify. So now if you see the incline, this is the height, am I right? So that means in the final part you have the height final. So whenever you have the height, you have the potential energy, right? So now what I have to do, I have to find one by one. We know the formula for the conservation of the energy, am I right? That means work, which is equal to, whenever the external work is applied to the block, the work which is equal to the change in mechanical energy, right, plus the change in thermal energy, right? And the change in mechanical energy is nothing but the final. It's a combination of the kinetic energy initial and final, right? So what you will get here? So you'll get change in kinetic energy plus change in potential energy plus this thermal energy also, right? So change in thermal energy, right? When you expand this equation, so this becomes kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial plus thermal energy. Clear? Now what I'm going to do, I'm going to separate the positive and negative term on side. So if you separate, what will happen? I'm going to move the initial kinetic energy and initial potential energy to the left hand side. Therefore the equation becomes W plus Ki plus Pi, which is equal to Kf plus Pf plus thermal energy, right? Now we have to substitute the value, right? So when the block is exactly in the bottom side, what is the work done here? So we have to consider the initial work is exactly 0. Clear? And also we have the initial kinetic energy. What is the initial kinetic energy? The initial kinetic energy value is 150 joules. And what should be the initial potential energy? If you don't have any height, your initial potential energy will be 0, right? If there is no height, H is equal, H initial is 0. So by that, everything will be 0. Am I right? And also, when the block reach the maximum height, the speed will be stopped. So your kinetic final energy, that means the final kinetic energy will be 0, right? So only, and if the block reach the maximum height, by the time you will get the maximum height, so you will get the final potential energy. And also we have to find what is the thermal energy. Clear? So now what I'm going to do, I'm going to substitute the value in this equation. The initial kinetic energy they mention as 150, because the rest of the work done and the potential energy initial is 0. So I have to discard that. So 150 joules, which is initial kinetic energy, which is equal to mgh final plus, And we already studied the rule for the thermal energy. What is the rule for the thermal energy? Fk, that means the kinetic friction multiplied by the distance. And what is Fk? In chapter number 6, we studied Fk, which is equal to Fn mu k, right? And what is our Fn? So you have to identify the normal force from the free body diagram. My normal force, which is exactly equal to the downward force. So that means my normal force Fn, which is exactly equal to our mg cosine theta. So I have to write this because the upward force, which is equal to the downward force. So here mg cosine theta multiplied by mu k. What is our mu k value? Better I can write it right now as it is, and later on I am going to substitute the value. So this is the value for the Fk, and I have to substitute this Fk here. By that your equation will become 150 joules, the left hand side, which is equal to mghf plus Fk. What is our Fk? Mg cosine theta multiplied by mu k multiplied by d also. Am I right? So that means mg cosine theta multiplied by mu k multiplied by d also. Now we have to find what is our height. Am I right? Because without this height final we can't. So I have to use this diagram. Brother, you have to see this diagram. This is of my opposite side. This is my hypotenuse. Am I right? So what we studied in the trigonometric, sine theta, which is equal to opposite side over hypotenuse, opposite side over hypotenuse. Here opposite side is hf, right, divided by my hypotenuse is the distance, right? The left hand side I have sine theta, right? Therefore my height final which is equal to d sine theta, real, correct? hf, which is equal to, so this d will come to the left hand side of the numerator. By that h final, that means the height maximum, which is equal to d sine theta. Now what I'm going to do, I'm going to take this value, I'm going to substitute here. So if you substitute, what will happen? You will get mg multiplied by d sine theta plus mg cosine theta multiplied by mu k multiplied by d. Left hand side you have 150 joules. Now what we are going to find, we are going to identify what should be the value for the d. So before that I'm going to take the common term outside. So what is the common term here? We can just take mgd outside, am I right? Because here also we have mgd and here also we have mgd. So I am going to take mgd as a common term. So inside the bracket you will get sine theta plus cosine theta multiplied by mu k, correct? On the left hand side we have 150 joules, and I have to rearrange this equation in terms of d. Therefore the d, which is equal to 150 divided by this mg, as well as this term will come to the denominator, am I right? So mg multiplied by sine theta plus cosine theta multiplied by mu k. Now I'm going to substitute the value. So once you substitute these values in this equation, we will get the answer for this question. Understand? So let's we substitute one by one. So 150 joules divided by the mass of the block. What's the mass of the block? You have to go back to the question. So the mass of the block is exactly 4 kilogram and the angle is 30 degree, right? And the mu k value is 0.36, right? So we have to substitute the value in this equation. So we have all these values, am I right? So I'm going to substitute one by one. So the mass of the block is exactly, the mass of the bundle is 4 kilogram multiplied by 9.8, and inside the bracket sine, what is the angle? 30 degree, right? So 30 degree plus cosine of 30 degree multiplied by mu k value. What is the mu k value? 0.36, right? So now I have to multiply and divide. So by that we will get the answer for the distance, how much distance the block is moving in the upside of the incline. So 150 divided by 4 multiplied by 9.8 multiplied by sine of 30 degree plus cosine of 30 degree multiplied by 0.36. So 4 multiplied by 9.8, I got 39.2 here. Sine of 30, because I got some error, it's exactly 0.5 plus cosine of 30 degree, I got 0.8660 multiplied by the mu k value 0.36. So I got the answer as 0.3118. So now I have to divide this value 150 divided by 39.2, so 0.5 plus 0.3118, got the answer as 0.8118. Now I have to divide this value with 150, therefore 150 divided by 39.2 multiplied by 0.8118. So I got the answer as 4.71 meter. So this is the answer for the last question. Clear? So we solved these 4 questions. So especially when you solve this question, when you solve the question from chapter number 8, you have to read very carefully, because in this chapter we are going to deal with the rule, the work done which is equal to change in potential energy, right? So please apply the rule very carefully and try to get the correct answer. Understand?